Big Muskie weighed 13,500 tons, stood taller than a 20-story building, and carried a bucket big enough to hold 2 Greyhound buses. It was built in Ohio to do one job at an almost impossible scale: tear away the earth above coal seams and move it somewhere else. Its boom stretched nearly 300 feet, and every swing could rip loose hundreds of tons of dirt and rock. The strangest part was not its size. Big Muskie did not roll on tracks, it walked. Hydraulic feet lifted the entire machine, shifted it forward, and set it back down, one heavy step at a time. Just listen to what a giant dragline at work sounds like. For years, this machine did exactly what it was designed to do. It moved mountains, fed power plants, and became a landmark of American heavy engineering. Then, after all that success, it was cut apart for scrap. So why destroy a machine that still worked? The answer was not mechanical, it was economic. In southeastern Ohio, the coal was not sitting in neat black cliffs waiting to be picked up. It was buried beneath hills. The Musking mine spread across thousands of acres in coal country near the Musking River, where Central Ohio Coal Company operated as part of American Electric Power. The setup made sense on paper: dig the coal, haul it a relatively short distance, and burn it at the nearby Muskegon River power plant to make electricity. But the valuable part was only a thin layer compared with everything above it. Miners called that covering material overburden. It was not just loose dirt. It could include topsoil, clay, shale, sandstone, and broken rock packed in layers over the coal seam. Before a ton of coal could be loaded, that entire lid had to be removed. That was the real mining problem. A coal seam might be worth a fortune once exposed, but if removing the earth above it cost too much, the coal might as well have stayed underground. The mine was not only competing against geology, it was competing against math. Every cubic yard of overburden had to be dug, lifted, swung away, and dumped somewhere that would not block the next cut. The faster and cheaper the mine could move that dead material, the more coal became profitable to recover. Smaller machines could do the work, but they needed more passes, more fuel, more labour, and more time. In a strip mine measured by the square mile, small inefficiencies became enormous costs. That is why the idea of Big Muskie was not born from a desire to build a mechanical monster. It came from a very practical question: how do you uncover coal when the landscape itself is in the way? The answer was a machine that did not dig coal first. It attacked the layers above it. Big Muskie was designed to stand on one side of a pit, throw its bucket far out across the cut, drag back a mountain of overburden, and swing it away in a single cycle. The mine did not need a bigger shovel for coal, it needed a way to erase the landscape above it. By the time Big Muskie was proposed, the mine's problem could be reduced to a ledger entry: cost per cubic yard, not cost per machine, not cost per hour. The number that mattered was how cheaply Central Ohio coal could remove 1 cubic yard of overburden and expose the coal underneath. If that number dropped, more of the seam became worth mining. If it rose, whole sections of coal turned into stranded value. This is where bigger actually meant cheaper. The fleet of smaller machines could spread out across the mine, but each one needed operators, maintenance crews, fuel or power systems, spare parts, and support equipment. Each machine also took smaller bites. That meant more cycles to move the same ground, more coordination, and more time before coal could be reached. Big Muskie attacked the equation from the other direction. One enormous electric dragline could do the work of many smaller units with a much smaller operating crew. Its bucket could carry an astonishing load in a single pass, and its long boom could place the waste material far from the cut without trucks constantly hauling it away. The machine was expensive, but it was not bought like a trophy. Big Muskie cost roughly $25 million, an extraordinary price for the 1960s. Building it took more than 200,000 man-hours. Those numbers only made sense because the machine was expected to work for decades, moving hundreds of millions of cubic yards of earth over its lifetime. The economics depended on scale. The larger the machine, the more overburden it could move per operator, per shift, and per dollar of electricity. Electric power also fit the job. A dragline did not need to race across the mine. It needed steady, immense force, repeated thousands of times. For a power company feeding a nearby generating station, that mattered. Cheaper overburden removal meant cheaper coal. Cheaper coal meant more predictable electricity costs. But there was a catch hidden inside the logic. Once the math demanded a bucket this large, a boom this long, and a walking mechanism strong enough to move the whole machine, ordinary manufacturing was no longer enough. Big Muskie could not simply roll out of a factory gate. It would have to be built like a steel building that somehow learnt to walk. The machine that became Big Muskie began as the Bucyrus-Erie 4250W, a custom dragline designed for one place, the Muskingum mine in southeastern Ohio. Construction began in 1966, but this was not a machine that could be finished in a factory and delivered to the customer. There was no road wide enough, no bridge strong enough, and no rail route that could carry it as one piece. Bucyrus-Erie had to manufacture the components, ship them separately, and turn the mine site itself into the final assembly floor. The parts arrived in a stream that made ordinary heavy equipment look small. Roughly 340 rail cars and 260 trucks brought in steel sections, motors, gears, cables, machinery housings, and the enormous pieces of the boom. Each shipment was only a fragment, but together they were becoming one of the largest mobile machines ever built. At the site, crews assembled Big Muskie in the open piece by piece using cranes, temporary supports, and huge bolted and welded connections. The base came together first, then the rotating machinery deck, then the house that enclosed the hoist and drag systems. The boom was built out in sections until it stretched roughly 310 feet from the machine, longer than a football field from end zone to end zone. When it was finished, Big Muskie weighed about 27 million pounds. Its highest point stood around 222 feet above the ground, about the height of a 22-story building. The bucket alone was large enough to hold 2 Greyhound buses side by side, but the bucket was only the tool at the end of the system. Behind it sat a steel body so large that people could walk through parts of the machine like corridors inside an industrial plant. Production began in 1969. By then, the Bucyrus-Erie 4250W was no longer just a drawing, a contract, or a pile of shipped components. It was a completed electric dragline sitting in an Ohio coalfield, too large to be transported, too heavy for wheels, and too valuable to remain still. Which raises the obvious question, once they built something that massive, how did they make it move at all? The bucket was the part everyone remembered because it turned the scale of Big Muskie into something you could understand in a single glance. It was not just a giant shovel. It was a steel container large enough to hold roughly 220 cubic yards of material, and when it was full, it could carry up to about 325 tons of earth in one scoop. That is not a truckload. That is closer to an entire small house worth of ground being lifted at once. But Big Muskie was not digging coal directly. Its job was to remove the overburden, the layers of soil and rock sitting above the coal seam. Once that covering was stripped away, other mining equipment could come in and extract the coal itself. Big Muskie was the machine that opened the earth so the mine could reach what was underneath. The process worked in a rhythm. First, the operator cast the bucket outward, sending it away from the machine on huge cables. Then the drag cables pulled it back across the ground, forcing the cutting edge to bite into the overburden and fill the bucket as it scraped toward the drag line. Once the bucket was loaded, the hoist cables lifted it clear of the cut. The entire upper works of the machine then swung sideways, carrying the loaded bucket through the air. At the dump point, the operator released the load and hundreds of tons of broken earth spilled out onto the spoil pile. Then the bucket went back out and the cycle started again. Cast, drag, hoist, swing, dump, repeat. This was the basic motion that made Big Muskie productive. Not speed in the ordinary sense, but volume. Every pass moved an amount of earth that would take a fleet of smaller machines much longer to handle. The bucket was the contact point with the ground, but the real work depended on everything behind it. The boom, the cables, the motors, the rotating deck, the counterweight, and the electrical power feeding the whole machine. So when people stood beside the bucket after Big Muskie was gone, they were only seeing the visible tip of a much larger system of forces. Big Muskie could not simply roll across the mine on tracks like a bulldozer. At 13,500 tons, the machine was too heavy for ordinary movement. Tracks would have spread the load, but even then, the pressure on the ground would have been enormous. In the soft, broken earth of a strip mine, that kind of weight could dig itself in, chew up its own path, and waste power just trying to move. So Big Muskie was built to walk. The word sounds almost ridiculous for something larger than many buildings, but the motion was real. Under the machine were massive hydraulically operated walking feet. When Big Muskie needed to relocate, those feet pressed down into the ground and lifted part of the machine's weight. Then the mechanism shifted the base slightly forward. The feet settled back into the earth and the machine dragged itself ahead. It was not walking the way an animal walks. It was more like watching a building perform a slow, deliberate push-up, then slide its entire body across the mine floor. Each step was short, controlled and expensive in effort. Big Muskie did not wander around the pit casually. Moving it was a planned event done only when the digging position had to change. At full walking speed, it could manage roughly 1/10 of a mile per hour. That meant a person could stroll past it with ease, while one of the largest machines ever built was still completing a step. But that slowness was part of the point. The walking system let Big Muskie move without depending on miles of rail and without forcing continuous tracks to carry all that mass across unstable ground. The feet created temporary contact points, took the load, shifted it, and released it again. When the feet came down, the mine itself seemed to answer. Just listen to the kind of weight that movement implied. That was the strange thing about Big Muskie. Most machines look alive when they are fast. This one looked alive because it was slow. The boom hung above the pit, the house rotated on its base, the bucket scraped the earth, and then, when the cut had moved beyond its reach, the entire machine gathered itself and stepped forward. Big Muskie did not carry a bank of diesel engines big enough to power its work. It was an electric machine fed by a 13,800 volt system that turned the mine itself into part of the power supply. That voltage ran into transformers and motors throughout the machine, driving the hoist, drag, swing and crowd systems that made each digging cycle possible. When the bucket dropped into the cut, it was not just gravity and steel doing the work. Electric motors were pulling cables, controlling motion, and converting power from the grid into movement on a scale almost no operator would ever feel anywhere else. That appetite shaped the schedule. Big Muskie used so much electricity that the cost of operating it depended not only on labour and maintenance, but on the price of power at the hour it was running. Crews often favoured nighttime operation when electricity could be cheaper, so the machine's rhythm followed both the coal seam and the utility rate. If the hidden logistics behind machines like Big Muskie are the kind of industrial stories you want to keep exploring, subscribe. Inside the operator's cab, the machine was less a landmark and more a workstation. The operator had to manage the boom, watch the bucket, time the swing, and coordinate each drag cycle with a view measured in hundreds of feet. One mistake did not mean a small correction. It meant a bucket larger than a small house was moving through the wrong part of the pit. A cycle began with the bucket cast out toward the digging face. The drag cables pulled it back through the overburden, filling it with earth and rock. Then the house swung, the bucket rose, and the load was dumped onto the spoil side, clearing material above the coal. Again and again, the same sequence repeated, controlled by people who had to make an enormous machine behave with precision. For 2 decades, that routine became one of the largest earth-moving operations ever performed by a single machine. Big Muskie stripped away hundreds of millions of cubic yards of overburden and exposed coal that fed power plants across the region. Its work was not one dramatic lift. It was the same electric cycle, repeated shift after shift, until the landscape itself had been rearranged. Big Muskie worked for about 22 years, and by the time it stopped, the totals were almost hard to keep in one frame. Depending on the source, the machine removed somewhere between about 483 million and 608 million cubic yards of overburden. That range exists because different reports counted the work in different ways, but the point does not change. Big Muskie did not just open a pit, it moved a measurable piece of Ohio. A cubic yard is not an abstract mining statistic. It is a block of material 3 feet wide, 3 feet long, and 3 feet high. Now multiply that by hundreds of millions. Load it into ordinary dump trucks, and the line would not feel like a construction project anymore. It would feel like a moving wall of earth, stretching far beyond the mine. Each pass of the bucket cleared rock and soil that had been sitting above coal for geologic time. As the overburden shifted to the spoil side, buried seams became accessible to smaller equipment, haul roads, loaders, and the rest of the mining operation. Big Muskie was the machine that made the coal reachable. Across its working life, it helped expose roughly 18 million to 20 million tons of coal. That coal supported electric generation and helped sustain mining jobs in the region, from operators and mechanics to rail crews, plant workers and suppliers tied to the mine's output. The visible result was not a single crater. It was a changed landscape of cuts, spoil banks, reclaimed ground, access roads and artificial ridgelines. Big Muskie turned repeated bucket cycles into regional geography. Places that had once been continuous hillsides became engineered terrain shaped by the logic of seams, stripping ratios and power demand. For the company, that scale was the machine's advantage. One dragline could do work that would have required an army of smaller machines, and it could do it for years. But the same scale also locked Big Muskie into a narrow world. It needed massive coal seams, cheap enough power, steady demand, and a mine plan large enough to justify keeping it alive. When those conditions began to change, its greatest strength became its weakness. By the late 1980s, Big Muskie was no longer just fighting rock, it was fighting the market. The coal it helped uncover came from southeastern Ohio, and much of that coal had a problem baked into it: sulfur. For years, high sulfur coal still had a place in the fuel mix because power plants were built around local supply, long contracts, and the economics of nearby mining. But that balance became harder to defend as air pollution rules tightened. The decisive shift came with the Clean Air Act amendments of 1990. Those rules put stronger pressure on sulfur dioxide emissions, the pollution linked to acid rain. Utilities had choices. They could install expensive scrubbers, buy emissions allowances, blend fuels, or switch to lower sulfur coal from other regions. For a giant dragline in Ohio, that policy change was not abstract. It changed what the coal was worth. Big Muskie had been designed around an older equation: remove enormous amounts of overburden, expose large quantities of local coal, and feed a power system that wanted that fuel. Once customers could meet their requirements more cheaply with different coal or cleaner burning sources, the advantage of scale started to shrink. At the same time, the machine itself was aging. A dragline that size did not simply need repairs. It needed specialized repairs, huge replacement parts, expert crews, and long periods of planning every time something major wore out. Its walking shoes, bucket rigging, motors, cables, controls, and structural components all carried costs that matched the scale of the machine. Then there was electricity. Big Muskie was electrically powered, and it consumed power on an industrial scale. When energy costs rose, every bucket cycle became more expensive. A machine built to win by moving more material had to keep moving enough material to justify the bill. Competition made the calculation worse. Smaller, newer and more flexible mining equipment could be deployed where needed, moved more easily, and matched to changing mine plans. Other coal fields could offer lower sulfur fuel, different transportation economics, or cleaner compliance options for utilities. Big Muskie was not obsolete because it failed at its job. It was in trouble because it had been optimized for one very specific mining economy. When that economy changed, its strengths became liabilities: its size, its appetite, its location, and its dependence on a shrinking market. And that left the owners facing a bitter question: what do you do with a machine too huge to ignore and too expensive to keep? On January 29, 1991, Big Muskie was officially retired. The machine that had once worked around the clock now stood still in the Ohio landscape, too large to move and too expensive to casually maintain. For about 8 years it remained there idle, a landmark of steel and cable that people could still point to and say, that was ours. But retirement did not solve the problem. It only changed the question. Keeping Big Muskie as a preserved monument sounded simple from a distance. In reality, the machine was more like a small industrial facility than a display piece. Its structure had to be inspected, corrosion had to be controlled, access had to be secured, massive moving parts, even when parked, still created hazards. A dragline built to survive mining conditions could not just be abandoned safely and called a museum. Then came the money. Any serious preservation plan needed financing not just for a one-time rescue, but for years of maintenance, insurance, security, engineering work, and public access. Local supporters, historians, and former miners understood its importance, but admiration did not pay for stabilizing a machine that weighed thousands of tons. The cost of saving all of it was on the same scale as the machine itself. There were also legal and environmental obligations tied to the mine land. Surface mining did not end when the last bucket was dumped. Companies still had reclamation duties, including reshaping land, managing drainage, and returning mined areas to approved post-mining uses. Leaving the dragline in place was not simply a sentimental choice. It had to fit permits, liability rules, property rights, and regulatory requirements. That created the painful tension around Big Muskie's final years. For many people in southeastern Ohio, it represented skill, jobs, engineering ambition, and an era when the region helped power the country. Former workers knew what it took to keep that giant alive. Visitors saw it as one of the few machines on Earth that could make a human feel tiny. But the industrial reality was brutal. Big Muskie no longer had a profitable job. It could not be moved to a normal museum. It could not be maintained cheaply where it stood. And saving only the memory was far easier than saving the machine. By the end, the decision narrowed to one hard conclusion. If Big Muskie could not work, and if the whole machine could not be preserved, then the giant would be cut apart. In 1999, American Electric Power began dismantling Big Muskie for scrap. The work did not look like a normal demolition. Crews were not knocking down a building or clearing away a broken machine. They were taking apart something that had once been assembled like a moving steel city. Decades earlier, Big Muskie had arrived in sections by railcar and truck, then risen piece by piece into the largest walking dragline ever built. Now the process ran in reverse. Cutters climbed onto the frame with torches. Steel plate that had once carried enormous loads was sliced into sections small enough to haul away. Cables, beams, ladders, housings, and machinery were separated from the body that had held them together for more than 30 years. Each cut made the machine less like Big Muskie and more like cargo. This was not an engineering failure. Big Muskie had done exactly what it was built to do. It had stripped overburden from coal seams, worked through punishing weather, moved millions of cubic yards of earth, and helped feed the power demands of an era. Its end came because the job was finished, the economics had changed, and no practical plan could keep the whole machine standing. That made the dismantling harder to watch. The same scale that had once made Big Muskie a triumph made it impossible to save intact. A machine built from transportable parts had become too large for preservation, so it was reduced back into pieces that trucks could carry. The giant that once walked across the mine now left the site one load at a time. For former workers, the cutting apart was personal. They knew the sound of the motors, the feel of the ground when the bucket moved, and the discipline required to keep that machine alive. To outsiders, it was a spectacle of scrap. To them, it was the end of a workplace, a craft, and a chapter of Ohio coal mining history. Not everything disappeared. Big Muskie's enormous bucket was preserved and later displayed at Miners Memorial Park, where visitors can still stand beside it and understand the scale of what once surrounded it. But the walking machine itself was gone. By the time the last major pieces were hauled away, Big Muskie had completed its final movement. Not another step across the pit, but a slow return from legend to steel. Today, the part of Big Muskie that survived is the part that once did the digging. Its bucket sits at Miners Memorial Park near McConnellsville, Ohio, no longer hanging from cables or biting into the earth, but resting on display as a monument. Visitors can walk up to it, stand inside it, and see the scale without needing an aerial photograph or a production chart. The bucket alone is large enough to make a person look small. That is what makes it powerful. It is not a polished museum object behind glass. It is scarred industrial hardware built for impact, abrasion, and weight. Every plate and tooth points back to the physical reality of surface mining, where coal was not an abstract fuel source, but something reached by moving entire landscapes. The bucket remembers more than Big Muskie. It remembers the equation that made Big Muskie reasonable in the first place: rising electricity demand, coal-fired power plants, affordable large-scale engineering, and a regional workforce skilled enough to keep a machine that size operating day after day. In that world, building the biggest walking dragline on Earth was not a stunt, it was a tool matched to a very specific problem. When that equation changed, the machine lost its purpose. Coal markets shifted, environmental rules tightened, mining methods changed. The land that Big Muskie had crossed was reclaimed. A giant designed for continuous production had no easy second life once the system around it moved on. That is the real ending of the story. Big Muskie did not disappear because its engineers aimed too high. It disappeared because the conditions that justified it disappeared first. The bucket remains because it can do what the full machine could not. It can stay in one place, hold memory instead of earth, and let people measure an era by standing inside the tool that defined it. And that leads to the final question behind machines like this. Sometimes the most impressive things humans build are also the most dependent on the moment that made them necessary. Big Muskie was not just a giant machine. It was the visible result of an economic equation that once made sense. Cheap coal, expanding power demand, huge contracts, and confidence that steel, cables, and human maintenance could keep up with the scale. When that equation ended, even the biggest walking machine on Earth became scrap. What survived was not the boom, the house, or the walking mechanism, but the bucket, because one piece was enough to carry the weight of the story. So the question is not only whether Big Muskie was impressive, it is whether machines like it should be preserved before their moment passes completely. If you think giants like this belong in museums, or if you think the bucket is the right kind of memorial, write your view in the comments. Thank you for watching. For the next engineering history story, keep watching and leave Big Muskie where it stands now. Gone from the mine, but remembered by an empty bucket.